Thank you, Tanya. Thank you for organizing this event with EJ. So I'm delighted to be able to just speak briefly about some of our research activity in the sensor space. Let me turn on the laser pointer. Uh, so this is just going to be, I suppose, fairly superficial, not a lot of details, but my information is below both my email and a website that contains relevant articles and information regarding our research activity. So I am with the electrical and computer engineering. This is just a brief biography. I'm also affiliated with the Texas Materials Institute, been at UT for about a decade. And we work mostly on two-dimensional materials and trying to explore these materials for diverse applications that could include nanoelectronics, information storage as a memory, and sensors and wearables, which will be the focus of today's overview. So our research has received several awards due to the hard work of many of the students and the innovation that we've brought to play. And we're also quite active on social media for the broader dissemination of technical knowledge. So some of our videos have received more than 100,000 views. So the basic center of my research activity is focused on two-dimensional materials like graphene. And these materials can broadly be viewed as atomically thin materials. They're the thinnest class of materials, crystalline materials on Earth. And there are hundreds of these materials. So the most popular is the graphite system, which is of course in all our pencils. And the beauty of these materials is you can cleave layer by layer from the bulk material. So the graphene is just a single carbon sheet of atoms that make up graphite. And so there are other kinds of 2D materials, MOS2, hexagonal boron nitride, most of them are less than a nanometer. And you may ask what makes them interesting for sensors. So besides the fact that they offer the maximum surface to volume ratio, meaning essentially all the atoms in these materials can participate in sensing, they also afford a variety of sensing modalities. You could do bioelectronic, biochemical, biooptical, biothermal, biomechanical sensing. And so all modalities of physical interactions are actually available with these materials. So I'll give some examples of just some of our research motivated by this broader image that shows that, for example, for biosensor applications, these materials can offer very diverse capabilities, all the way from the invasive to non-invasive, biophysical, biochemical, environmental, and so on and so forth. In our research, because of our IRB approvals, we've mostly focused on non-invasive applications. So one of them is the so-called graphene electronic tattoo that we invented here at UT Austin. We can place this monolayer atomically thin material on the skin. This is a video showing a transfer of this material from tattoo paper, a process that we developed, onto the skin. These are very, very flexible atomic materials, and so they're very conformable to the roughness of the skin, and they last several days on the skin. What can you do with this material? So the application space is quite broad, all the way from mobile health, which has been a key focus of our activity, to human-machine interfaces, athletics, and fashion. So for example, I just showed two sets of data here. We can do electrophysiological monitoring with the tattoo on the skin. This is showing data from the tattoo graphene materials compared to conventional standard. We see that, in fact, the signal to noise ratio is better, even though these materials are atomically thin. You can do also physiological measurements like temperature, skin temperature sensing. Obviously, this is very important for health reasons. And so these are just examples where I have a wealth of knowledge and data in this space. Another area of research is that we've been focused on for diagnostic sensing. This is a grant that we have from the federal government. For example, we developed a platform to do selective sensing of, for example, virus diagnostics. And this uses a well understood process where you functionalize a graphene, in this case, the graphene material, which is a transistor, you functionalize it with the antibody of interest. That antibody gives you the specificity to the target. So if you functionalize it with the COVID antibody, then it becomes sensitive to the COVID virus. And so the electronic properties such as the resistance will change depending on the interaction with the species. And you can do the same, for example, our earlier work, we functionalize it with the antibodies of ferritin, and then that allows us to monitor, for example, iron deficiency towards the application for pediatric iron deficiency. So very general platform, we're very active in this and doing detailed studies of these kinds of sensors. And perhaps the last example I'll show is for any real system, one needs to have an integrated platform. That means you have your sensor integrated with the readout electronics. So this is previous work by my former PhD student where we're able to integrate this, for example, graphene gas sensor in this particular case with the silicon readout electronics. The silicon is of course very important to provide you all the capabilities of modern electronics, while the graphene gives you the huge surface to volume ratio and the platform for functionalization. So this is a silicon chip in normal silicon foundry technology. We have the entire process that we can place this on top of the chip. Others have now started doing this as well. This is beautiful work from one of my colleagues, Frank Coppins, where they developed a graphene optical sensor, essentially a graphene camera, also integrated on a silicon chip. So I think those are the few examples I wanted to just highlight today. Anyone interested is of course welcome to ask questions. We're always looking for collaborations and partnerships. And again, my email and phone and website is listed on this page. Thank you all.